So physics is a physical science. And we break it down into a number of areas. There are only a few of these that we're going to get to in here. Mechanics is our primary focus. And mechanics is motion, movement, forces, work, all of those things. This is classical Newtonian stuff. It has not changed. There are no groundbreaking discoveries in mechanics. Nobody is doing intensive work to understand mechanics better. No, we got it. You've done some of this in physical science, motion, kinematics, and you'll do this with a whole bigger emphasis on the math here. And this is probably a good half of our year. Thermodynamics is the next area. We don't get there at all. I would love to do thermodynamics in my dream physics class. We have a unit on thermodynamics, and we build heat exchangers of some sort. We do solar preheaters for water tanks, something, but yeah, we don't do that. It's how materials exchange heat. And it's something that bridges chemistry and physics. I was just talking to a guy who teaches chemistry at Kent, and he was talking about doing some sort of, it's really early thermodynamics work in their Chem 2, I think, their Gen Chem 2. So it's looking at how materials exchange heat, how heat moves through systems. Vibrations and wave phenomena, we do a little bit with. So if you're keeping score, mechanics, yes. Thermodynamics, no. Vibrations and wave phenomena, a little. And this gets down to light, sound, all of that. Lenses, mirrors. We do more with mirrors than with lenses. And we do simple harmonic motion stuff. Optics, we do a little bit. That links to wave, vibration, and phenomena. It's how light travels. So, a little bit. Electromagnetism. This is the other section that we do cover. Electromagnetic waves, the behavior of electromagnetic waves, magnets, electricity, circuits, the movement of electrons. These last two are the cool, sexy parts of physics. Years ago, they may still offer it, Kent State at Liverpool and Salem had a class called 7 Ideas That Shook the World, and I always described it as cocktail party physics. And I would have students come back and go, I'm taking physics at Kent. I'd say, no, you're not. You're taking 7 ideas. And it's the cool stuff. It's the stuff that you can drop at a party and everybody goes, wow. We don't get there. We don't do it. It's above the pay grade of this class. And it doesn't well prepare you for college physics, which is the goal here. Relativity is all that stuff that Einstein talked about. It's objects that are approaching the speed of light. It's objects moving at very high speeds. It's also the way that particles behave and move, like subatomic particles. And then we have quantum mechanics. Do not confuse that with mechanics. It is motion, but it's not motion of you, me, a train, a bus, a rock that I drop, something that rolls down a hill. It's the motion of subatomic particles. And here's the weird part. So we have this wonderful thing in science. It's the universality of scientific laws. If you had me for chemistry, you've heard me say laws don't have to explain a thing, and somewhere I have art from a student that says that. Hypotheses are working explanations. Theories are hypotheses that have not yet, that have been attacked repeatedly and not fallen. Laws don't really explain anything. Hypotheses and theories tend to explain how things work. Laws tend to be descriptive. So, law of gravitational attraction describes it mathematically. We can calculate it, we can compute it, we can predict. It doesn't explain why gravity works. We don't know why gravity works. Rubber bands? Quantum, so this universality idea is that laws of the universe operate in the same way all the time, everywhere, at all times, and they always have, and they haven't changed. It's not selective. Gravity doesn't work one way here and one way there. No, it doesn't work at all over here. They are universal and unchanging. Great. So we've had all these ideas behind mechanics for hundreds of years. Kepler and Newton worked out a lot of them. So everything behaves that way, right? We have laws of attraction, we have, we can describe forces and interactions. Great, and then we got down to subatomic particles. And it turns out at the subatomic level, things don't always behave in ways that are covered by classical Newtonian mechanics. So it turns out that the laws appear to be different at the macro and at the micro level. Well, that's a problem. And so really again, the cool, sexy part of physics is trying to work out what the umbrella is that explains why that is. Because the assumption is that if we buy into this idea of the universality of physical laws, there is some umbrella set of laws that governs that behavior. So in fact, these things are all complying with the same laws. They just appear different at different levels. So it's cool. It's mind-blowing. It's awesome. We don't get there. Way above my pay grade. I'm trained as a biologist with a minor in chemistry. I've been teaching physics for 7 years. This is so far outside my pay grade, I can't even see it. That's okay. Go read a book on it. Cover the chapters at the end of the book. It's neat stuff. Read anything by Brian Greene. Watch The Elegant Universe. It was a PBS 3-part special covering interesting ideas about these things, but we don't do it here. I'm so sorry. So don't confuse mechanics and quantum mechanics. Insert conversation about scientific methods here. We won't get to do as much as I would like in here with experimental design. You will do a couple, I call them inquiry labs. My physics students tend to call them nightmares, where you are developing your own methodology, and I am helping you pick and pick and pick and pick until it's good. One of the things that's heavily used in physics in terms of experimental design are models. And we want to be careful with the word models. Everybody knows, I think, that this is a model. That's a model of the land masses on our little planet, Earth. And there are different models for the land masses on planet Earth, but a map is a graphical model. That's all it is. If you draw a map of getting from here to the Rogers Sail, that is a graphical model of the territory between this spot and that. We tend to think about that. It's visual, it's graphical, it's easy. We also tend to think of things like this. It's an architectural model. It's a physical model. It's easy to understand. Who here has ever built a model? Airplanes, space shuttles, rockets? No? A couple of you, okay. I built a model space shuttle in the 5th grade. It was beautiful. I don't know what happened to it. Those are physical models and graphical models, and they're easy to understand. What's a little more complicated are mathematical models. And there was a book I read years ago by a climate scientist whose name I cannot remember. And he talked about having an undergraduate run up to him who was starting in climate studies and said, "Can I please see the climate model?" And he said, it's not a physical model. There's no physical model. It's a computer program that generates data sets which interact in one another. It can be represented graphically, and this is actually a climate model, or part of a larger climate model. It's a representation of a piece of the data contained in a climate model. A model is just it's a way things fit together. You have mental models of your world. You have mental models of chronological events. You wake up in the morning and you have a sense of where you will be at different points in the day. That is a mental model of chronological events. In science, we tend to use mathematical models, especially in physics. Physical models are useful. We do use them. Globes and maps are physical models. Actually, how many of you know what or where that is? Anybody? That is the Beaver Valley Power Station, Unit 2. My dad worked there for years. Anybody have family who works at Shippingport, Beaver Valley? Okay. It was the first plant at Shippingport. Unit 1 was constructed in the 1950s. It was the first nuclear power station in the U.S. Unit 2 was constructed in the 70s and went online in the early 80s. And at Shippingport, my dad was on the speakers team, and they used to do tours. And they don't do the tours the way they used to. I would love to take you guys. But one of the features of the tour used to be what they called the model room. And it was about 4 times this size. And it was an enormous plastic architectural model of every single pipe, valve, ladder, platform, wall, ditch, everything in that entire plant. And the figure that was quoted, and this was in the 1980s, because I used to get to go on tours a lot, was that it was $2 million worth of plastic. It's a lot of money. And, you know, I remember on tours people would say, why would they spend $2 million on a plastic model? Why? Because it's cheaper than getting halfway through construction and realizing that those two pipes, which appear to be in different locations on a two-dimensional drawing, are in fact occupying the same space. Oops. So $2 million of plastic is a great investment. But again, that's a physical model. Here, we are going to think more about the mathematical models. Though like I said, we do make some physical models. The other thing that we see in physics, and this is a little bit different, it's not something that we see so much in chemistry or in the life sciences, are thought experiments. And this is one of those things Einstein was well known for and famous for, was his thought experiments. And in a thought experiment, you're literally thinking through what happens to this if this happens. And so a lot of the quantum mechanics and relativity stuff involves thought experiments. They are all light years above my head. It's not a good joke, but it's the best I have this morning. Controlled experiments are something else. We don't see those as much in physics. We can do them in mechanics. And in a controlled experiment, of course, and you've known this since 9th grade, you've got a control group and experimental group. Only one is getting treatment. Okay, so those controlled experiments are where you've got, again, control group, experimental group, only one gets the treatment so that we have a valid means to compare. You should have picked this up in chemistry. The dimension is the thing, the kind of quantity that's being measured. Length is a dimension, mass is a dimension, time is a dimension. What dimension are you measuring? The units are the calibrated items which can be used to compare the dimension of which you are taking a measurement with some standard. And dimensions and units have to line up. So, you can tell me if you think I have a career ahead of me as a cartoonist. Yes, I drew this. I'm so proud of it. Should we be worried? I mean, she left quite a while ago. How long has she been gone? About 30 meters. Ha, 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 ha. That's okay. You don't have to laugh. I know I'm funny in my heart. That doesn't make any sense to us when we hear it because the units don't agree with the dimension. If we're saying how long has someone been gone, we know we're talking about time, so the units have to be a unit of time. Similarly, if we are measuring volume and we give volume in kilograms, that makes no sense whatsoever because kilograms are a unit used with mass. Yes, sir? Okay, page 12 in your physics book. If you would be so kind, if you would like to grab a physics book, go for it. If you have your physics book, this is the time to pull it out from underneath your desk. Oh, wait, there's no place to put it. You're going to find this table of powers of... So, SI prefixes, their abbreviation, and the power of 10 which they represent. Learn it. The ones that are highlighted here, pico, nano, micro, milli, centi, yeah, forget deca. Who uses deca? Kilo, mega, giga, tera. I expect you to just know. Okay? I will feel that those are free game to use on a test without clarification, and I expect, and okay, if we're being realistic here, which ones do we use most? Kilo, mega, micro, and milli. Those are really the ones we see a lot of. But all of these, pico, nano, micro, milli, centi, kilo, mega, giga, tera, I expect you to be familiar with. So I'm not going to give you the power of 10 for that. If you watched the little refresher video on doing conversions with exponents, if you're not feeling real confident, I can post some more resources. It is really important to get in the habit of using those exponents because of the higher math that we start to do. And I'm trying to think of examples where it's do or die, but it's a good habit to be in, especially if you're going on to higher science courses. You're going to use scientific notation. It's a tool, it's a functional tool. If you don't use the tool, you don't know how to hold the tool. You know, I'm imagining a hammer that somebody's holding by the very end and swinging wildly. Get used to using the tool and you become proficient with it. Same with conversions. Okay, so I have 714.2 megagrams. I want to convert to centigrams. This is factor label. This is from chemistry. You know how to do this. What always goes in the first box? Your given. And in this case, our given is the 714.2 megagrams. Make sure to include your units. Because you're going to be using scientific notation, I find it significantly easier to convert everything to scientific notation. I am terrible at moving decimal points. It is how I am guaranteed to screw things up. Oh, am I going this way? Am I going this way? Does the number get larger or smaller? If you're a rock star at it, bless your little heart, you're ahead of me. So I try to make it as dummy-proof for myself as I can, and the first step to that is converting everything to scientific notation so I don't have to move decimals. So that makes this 7.142 times 10 to the second megagrams. When you're doing conversions using powers of 10, it's a little different than if you're doing them using whole numbers. So rather than putting in 1,000,000 or 1,000 or 100, because you can't do that when you get up to gigas and teras and stuff. You want to make sure, of course, this is scientific, or this is factor label, so you want your units to match. You know megagrams will go here, and you know that your base unit will go there. I recommend always going through the base unit. There are ways to short circuit that, but that's where I tend to foul up. And I love math. My dad was a math teacher. He was the best math teacher I ever known. I've been doing algebra since I was like 8. I love math. That said, I make stupid mistakes. I make lots of stupid mistakes. So in a long lifetime of doing and loving math, because I hate those stupid mistakes, there's nothing more infuriating than understanding the larger theory and making really dumb mistakes and tripping over your own feet. Because that seems to be my specialty, I have developed some techniques for avoiding the common stupid mistakes. So use them, ignore them. They're just what works for me. I always go through base unit on these. So we want the units to match, we want the base unit on top, and here's the other thing. The power of 10 always goes with the base unit. So in this case, the power of 10 is going to go with grams. What is the power of 10 for mega? Who's got it already? You got your book out. Okay, go for it, Wyatt. 10 to the 6th. So 10 to the 6th grams is 1 megagram. Okay. Now I want units to match. I want to end up in centigrams. That'll be my last square. And again, I want a 1 in front of the prefixed unit, 1 in front of the centigram, and I always want my power of 10 in front of my base unit. So, power of 10 for centi. You want to take it? 10 to the negative second. What this gives you is the ability to do this really fast. 7.142 times 10 to the 2 plus 6 minus negative 2. And if you're not familiar with the rules for dividing and multiplying exponents, you can refresh on that, and I'll be tutoring probably Tuesday, Thursdays. Okay, so that gives us 7.142 times 10 to the 8 times 10 to the 10th. And that's our final answer. You recall that scientific notation always has to be a single number in front of the decimal, followed by as many numbers after the decimal as are appropriate based on your sig figs. Easy peasy? Cool. That's one of the easy conversions. These are really straightforward. So I call these bigger, badder conversions because they're not straight up units. We're dealing here with a derived unit. We're dealing with volume measurements. And there's one pitfall which people fall into, so we're just going to walk around it and make note of it. Again, given always goes in the first box. I'm going to convert this to scientific notation because it makes everything simple. 4.15 times 10 to the second cubic meters. Again, my units have to match to cancel, so I'm going to put cubic meters there. And I'm already in a base unit. I don't have to go through base. I can go straight from cubic meters to cubic millimeters. Cubic millimeters. Now here's the tricky part. 1 cubic meter is 1 meter by 1 meter by 1 meter. We're talking about 3 dimensions now. So the number of millimeters that occupy that space, the number of cubic millimeters, well, it's 10 to the third this direction, 10 to the third that direction, and 10 to the third that direction. That cubed is the thing that you want to pay attention to. So the trick that I have found to prevent myself from making the stupid mistake that I usually make is to sort of replace this mentally with 10, whoops, I just did that wrong. Well, that was stupid, Moser. See? The 1 always goes in front of the 1 with the prefix. So I kind of mentally replace this cubic meters with 10 to the negative third times 10 to the negative third times 10 to the negative third. And that's just the way that I remember that I'm actually looking at a cubic unit. So I put that in as a three bang. So now I have 4.15 times 10 to the 2 minus negative 3 minus negative 3 minus negative 3. I did run out of room for that. I apologize. So that's going to be 3, 6, 9, 11. So we're going to have 4.15. Okay. Times 10 to the 11th cubic millimeters. Okay, get out of here. Tomorrow when you walk in, be ready to hit the ground with your lab. And I'll post some practice problems for this if you feel you need them. If you don't need them, don't do them.